So we could begin with, the notion of two groups, right? And it really doesn't matter if we have, lone pairs or anything like this, but we're just talking about two groups on either side of the central element. And as an example of that, we had beryllium chloride. This is an example we talked about originally with two groups. And I guess I should say, both atoms and lone pairs, right? So we're not really discriminating anymore between molecular geometry or electronic geometry. We're talking about something completely different here. So this is, this idea of a hybridization. So if we look at the beryllium, for instance, the beryllium, might look something like this. If we consider beryllium from the periodic table, its valence shell of electrons is the 2s. Right, and this is the configuration that we have. And going forward, right, we know from our earlier conversations that we should have something that's going to look like this from Lewis dot structure, as well as within the VSEPR structure as well, right? This is a linear molecule, and it has those two electrons that the beryllium is sharing, one to each chlorine. But if we look below, the beryllium just has these two electrons actually already paired up in the 2s, so how does it actually encompass the binding? Well, it needs to hybridize. And it basically needs to hybridize as many orbitals as there are groups. And maybe we should be a little bit more specific, with those groups idea of being, atoms or lone pairs. If we look above, we see we have two groups. So we need to hybridize two of those valence orbitals. So if we come down to, the beryllium, let's write it again as far as its valence shell with those two electrons in the 2s. Right now it needs to hybridize. And it's going to hybridize two orbitals to do this. And so here is one orbital, and then here is another orbital. And that's going to change the orbital set that we have now in terms of this idea of hybridized orbitals for sigma bonding, as well as then, the possibility of non-hybridized orbitals as well. And so these two that we have here are being combined, and they're being made into sp hybridized orbitals, or sp hybrids. At the very top, we still have the 2p orbitals that are left over that we haven't really touched. So we start with 2s and 2p. If you count the orbitals, there are 4 of them there. And we still have 4 orbitals here on the opposite side of the hybridized arrow, 2 of which that we've combined and created 2 new orbitals, and then 2 that we have left alone. So here is where we have our hybridized orbitals, and that's where we can make sigma bonds. And at the very top, we would have this idea of non-hybridized orbitals, and that would be for pi bonds. We're not quite yet there to pi bonds, but that's coming our way, so might as well get used to seeing that. And now if I look and put in my electrons according to Hund's rule, right, and the off-ball principle, I do something like this. And so we find in that hybridization process, now we have 2 new bonding orbitals. We now have 2 bonding, hybridized orbitals. Each with a, with an unpaired electron to now participate in our bonding scenario. So let's look at that idea a little bit further in the sense of, I could start with maybe some orbitals and just kind of look at what we're doing with that process. Right? We had the 2s orbital, and we have kind of this p orbital, which we see here, and basically we're combining them in this kind of mashup in this hybridization process. And what that creates is 2 new orbitals. One of them looks like this, and the other looks like this. And so each one of these is an sp hybrid orbital. Right? This hybridization is a combination of the 2s and 2p wave functions. And so that's what's setting the stage then for the beryllium to actually be able then to participate in the bonding. Where beryllium is going to have, one lobe out to the right. It's also going to have one lobe out to the left. Both of these are the sp hybrids. Also notice that they're 180 degrees apart, and each one is going to have an electron in it now because of that hybridization. And now we then have the chlorines on the outside of each one of those sp hybrid orbitals, and now it's got its lobe coming in to share, right? Remember, we have a sharing of electrons, so the chlorine is bringing its electron into the mix, and then it also has its other lone pairs as well. And so these sp hybrids, remember, these are our hybridized orbitals, and they participate in sigma bonds. Remember, that's our first connection. So that allows us to have then, our beryllium in the middle. We have our two sigma bond connections to then the chlorine atoms, and that's that idea of valence bond theory, is how the beryllium took those two s electrons and then somehow split them up so that each one was unpaired to then participate in the bonding with beryllium chloride. So that's the new take really on this model, is how are they changing their valence shell electronic configuration to participate now in bonding scenarios. The hybridization also complements the geometries that we talked about with Vesper, here being our two sigma bonds. And again, we still have that 180 degree angle. So, this idea of the valence bond theory, or, hybridization, complements the electronic geometry. In this case, right, linear. So that's two groups, and starting to now develop this notion of hybridization. Let's continue to three groups. Right, with three groups again, we're talking about both atoms and lone pairs in that mix of groups. And we had used an example of boron trifluoride, where we put together the structure rather quickly here. Also just trying to reinforce the geometry that we should see in this molecule. So we have this particular structure, but if we look at our boron, again in terms of its valence shell, it looks like this. So again, there's our valence shell electron configuration. And we need to hybridize. And just, to just kind of reiterate, we hybridize the same number of orbitals as our groups, right? And the groups are atoms or lone pairs. So we're still following that motif, and so if we count up, right, we have 3 groups, so we need to hybridize three orbitals. So if we come back down to, that notion of the boron, we have our valence electrons, and we need to hybridize now 3 orbitals in going forward. And so that means we'll have 3 new orbitals, and then 1 that's actually left over. Our leftover orbital is that 2p orbital, and then the other 3 are known as sp2 hybrids. Or singular. So these 3 are coming from our combination of s and p orbitals to create these new orbitals. Below we have our hybridized orbitals, and that's where our sigma bonds are going to come into play. And up top we have our non-hybridized orbital, and that's what we will use eventually for pi bonds, but we're just not there yet. But just it's this idea of orbital conservation, that we started with 4 orbitals, and we should still have 4 orbitals, which we do here. So the boron has hybridized, right, that idea of 3 orbitals to make the 3 bonds, and now we put electrons in them, we end up with those 3 electrons. They're now unpaired, right, and ready to actually now participate in bonding via sigma overlap, and then making those single bonds that we know we have to form between the boron and the fluorine. So here, the hybridization is now a combination of 1, s orbital and 2 p orbitals. So we have this notion of our s orbital, specifically the 2s. And then we have our notion of our 2p orbitals. So they look a little different in the sense of their orientation, right? As far as we have 3 of them, one in the X plane, one in the Y plane, and then there's the third one, which is not pictured here, in the Z plane. And so those combine to now make our sp2 hybrid orbitals. And you end up with one that looks like this. We end up with one that looks like this. And then we also end up with one that looks like this. And so those are the 3 orbitals we get from now these combination of the P and the 2s. And if we overlap that, that's what gives us our actual shape. So we have our boron, and it has a lobe above for bonding, a lobe off to the left, and a lobe off to the right. And each one has that electron within. And now we have our fluorines there to bond with those hybridized orbitals. And so we could write our fluorine at each one of those lobes. Each fluorine still has its lone pairs. And then we have an electron from the boron and an electron from the fluorine. And so those are our single bonds, and it's also, again, kind of keeping up with that notion of our angle is still 100 degrees Celsius, still supporting that. And then we have, 3 sigma bonds as a result. So our boron maintains that trigonal planar shape. Here are our 3 sigma bonds from the hybridized orbitals that we have, right? These sp2 hybridized orbitals. And that gives us our geometry as well, still supporting that notion of 20 degrees. So supports, right, the electronic geometry of trigonal planar. So as we go from 2 groups to 3 groups, and now beyond, that means we just need to hybridize more and more orbitals in order to do that. If we move to If we move to 4 groups, right, that means we're going to have to hybridize 4 orbitals. So we can look at, methane as an example. right, we can put methane together with its tetrahedral geometry to look like this. But again, it's this idea of how does it do it? Carbon now has 4 valence electrons, so here's its valence electron configuration. And so we need to hybridize in order to have these electrons unpaired to participate in our bonding motif. Here with our 4 groups, right? That means we need to hybridize 4 orbitals. So in looking at our carbon right now, we're hybridizing all of them. Because that's as many as we've got. We got 1, 2, 3, and 4. And so all those are now turning into sp3 hybrids. All right, so each one of these is an sp3 hybrid. Looks like I can't fit them on there. So here's something that looks like that, and that's again that combination of now all of these valence orbitals. And then that's what allows us now to have all these electrons, those 4 electrons, actually unpaired. And so this is where we're going to get our 4 sigma bonds. There's no extra orbitals for pi bonds or anything like that. Again, we're still a bit ahead of us right with that idea. But we can make now 4 bonds to those 4 hydrogens that are around the carbon. So this is where this combination of, our S and our P's, this starts to get, more complicated as we go. So here we have our 3 different p orbitals now. We have our 2s, and then here are our 2p, just as far as the orientation is concerned. And now that's generating, this type of overlap where, where that geometry that we observe is actually coming from. Where now we have, 2 lobes that are in the plane. We have 1 lobe that's coming out at us. And then we also have 1 lobe going away from us. Right, and so each is a sp3 hybrid. And each one's now going to have an electron, within it. So that carbon atom is going to have a lobe above, a lobe off to the left, a lobe coming out at us, and a lobe going away. And each one is going to have an electron within it. And so that now allows for that overlap between it and now our hydrogen atoms. Each of the carbon's electrons is singular, right? In each one of the sp3 orbitals. And then each hydrogen is bringing in another electron to actually make the bonding pair. And we're still within that idea of the geometry of 109.5 degrees. So our carbon atom is going to have 3 sigma bonds. One coming out, one going back, and then 2 that are actually in the plane of the page. And so, just like before, and we're going to find this is very much a constant, it still supports the tetrahedral electronic geometry. Let's look at another example of 4 groups with ammonia. With ammonia, we end up with a structure that will look like this. Where now notice that we have, still this idea of a tetrahedral geometry in terms of electronic geometry, but we have a lone pair as opposed to like an actual atom. So just wanted to show an example of this, that the hybridization motif doesn't change even if there's a lone pair that's actually there. So with our nitrogen, we have this representation. And as far as, our hybridization motif, we still have this notion of 4 groups. So that means we need to hybridize 4 of those orbitals. So if we, do that process of hybridization, right, we're going to hybridize all 4. And so here we have our sp3 hybrids. Right, we're still hybridizing 4 of the orbitals that we actually have. And if we start putting electrons in, right, we would have something that looks like this, right, where we have 3 that are, unpaired, and then we have 2 that are paired. And so this is where we would get our 3 sigma bonds. And here is our lone pair. Right, so it's still the same type of organization in terms of that. So our nitrogen would have those 4 lobes, just like our CH4 example. And then it would have 2 electrons in 1 because of the lone pair. And then it would have 1 electron in the other 3 lobes, and that's where its sigma bonding is going to occur. And so we end up with our nitrogen now overlapping its hybridized orbitals with then the hydrogen atoms. And so we have the lone pair at the top. Nitrogen has its extra 3 that are unpaired, and now the hydrogen's bringing its extra 1. And so that's where our geometry actually comes from then, as far as the ammonia. Right, we still have that. It's really not a bond, right? It's just a lone pair. But it's still part of that reorganization that's occurring to try to get these groups as far apart from one another as possible. And remember, we have that slight compression that's occurring because of how big the lone pair lobe is really actually relative to the others. And so we have our 3 sigma bonds, and this still supports the tetrahedral electronic geometry. Even with a lone pair or pairs. So we just count all the groups up. We then hybridize the approximate number of orbitals with the number of groups, and now that's the shape that we talked about prior as far as the electronic geometry is concerned. Going now to 5 groups. We looked at phosphorus pentafluoride as an example. Remember, we had to expand the phosphorus octet, so it has everything unpaired to bond to the 5 fluorine atoms. We have that trigonal bipyramidal electronic configuration that we're seeing here. And so now realize that we're going into this idea of expansion. so far we haven't brought in the notion of d orbitals, but with S and P, there's only a total of 4, so you can never get past 4 bonds in using s orbitals and p orbitals. So in order to get past 4, to get to 5 and 6, that means we need to use now d orbitals in the mix. So we're now talking about elements that can expand their octet right there in that principal quantum level of n being greater than or equal to 3. So if we look at our phosphorus here, we'll find that it has a lot more to offer in terms of its valence shell. It has 3s, 3p, and 3d orbitals. Now realize that this is our, valence electron configuration. But also, in order to bond and hybridize, to do that bonding process, right, there are basically now 5 groups. So that means we need to hybridize 5 orbitals as a result. So we're still doing the same motif, which is that when we have now more to actually play with. So that means we could do 1, 2, 3, 4, and now 5 orbitals. And so what we have now is 1, 2, 3, 4, 5 orbitals here. We still have 1, 2, 3, 4. These are the 3D set that we haven't changed from above. And here we're now undergoing that process of, hybridize, 5 orbitals to make bonding orbitals. And so now this is called sp3d. And so these are all sp3d hybridized. If you're an old dog like me, I learned this as DSP3. So, I'll accept either or. But we have, with the phosphorus, there's 5 electrons. So how does the phosphorus expand? Well, that's how it actually does it. It actually incorporates the d orbital set into its hybridization motif to make bonding orbitals for the fluorines. And so now we have those 5 unpaired valence electrons to now bond with the fluorine. And so going a little bit faster here, the shape is just what we would expect so far. That these hybridized orbitals are going to have that configuration that we have for the trigonal bipyramidal structure. So there's our phosphorus with its 5 unpaired electrons, and each one of these is an sp3d hybrid or hybridized orbital. And so that's where now we can, do our, overlap with the oops, with the 5 fluorine atoms that we actually have. And so now we have, the 2 electron motif. We have the 5 in the dsp3 or sp3d hybridized orbitals, and now the fluorine is contributing its electron as well to actually then make the actual bonds to the phosphorus. So we end up with our phosphorus now having these 5 sigma bonds coming out from it to bond to the 5 fluorine atoms. And just like before, this still supports our electronic geometry. So same notion. With 6 groups, now we're just at the octahedral state. And so we were using an example of sulfur, hexachloride as a way to represent this. And this is where we would have to have an expansion to occur. Sulfur would have to expand all of its orbitals in order to have the 6 unpaired valence electrons to bind to the chlorine atoms. So here would be our electronic geometry of octahedral. And so there's our 6 groups. So looking at the sulfur, right, we know it has to expand in order to do this process. And so here's our valence shell, which looks like this. And so now we need to hybridize, 6 orbitals in order to do this. If we look at the top, we have 6 groups. All right, that means we need to hybridize 6 orbitals. So that means we just have to tack on another d orbital to the process. So if we do that hybridization process, now we're going to end up with 4 orbitals that we haven't done anything to. Or I'm sorry, 3 orbitals that we haven't done anything to. And then we have our 6 that we've combined. So now we have sp3d2. So we have these sp3d2 hybridized orbitals, and again, being the old dog, got to complain, right? I was taught it always was d2sp3, but we get the same idea, same number of orbitals in the d, the s, and the p set, and now we have basically a singular electron to now participate in our covalent bonding, right? Our sigma bonding. So the sulfur is going to have those lobes to just mimic really that octahedral geometry. So we would end up with something that looks like this. Each orbital now that's hybridized has 1 electron in it. And these are all of those orbitals that we just constructed, all sp3d2 hybridized. And so that allows us to then really put into terms of structure. I'm going to kind of skip a step here just to kind of represent, I think we got the flow of it now. We end up with a structure that looks like this, with our chlorines around the outside, in that octahedral electronic geometry. And so we have those now 6 sigma bonds within the molecule. And that's where that, octahedral shape kind of comes from, as far as that electronic geometry is concerned. So that's, the idea of the first connection. Like all of these examples that we talked about were a first connection, either making sigma bonds or maybe having a lone pair in the mix, but that didn't, we didn't get into the non-hybridized orbitals, right? Remember, we have sigma bonds, which are resultant from hybridized orbitals. Lone pairs, even though it's not a bond, goes within that kind of, first connection or, first level of connectivity. So that's also part of that hybridized motif. But what we haven't talked about yet is what about the non-hybridized orbitals, and getting now into other layers of bonding like double bonds and triple bonds, and now this new type of bond, which is the pi bond.